Would this also be 1?
It is, yeah, because cotangent is cosine t over sine t. Tangent is sine t over cosine t. Lots of cancellations there. Yeah, you get 1. All right, so 31. 31 is a known, kind of a known trig identity, kind of. There's 3 that you have to know. Sine squared x plus cosine squared x equals 1. And then 1 plus tangent squared x equals secant squared x. 1 plus cotangent squared x equals cosecant squared x. So these are the 3 that you have to know. They're on that review sheet. If you want, I can send that over again. So what they're expecting you to recognize is when you see a squared, you're supposed to go for the one that kind of matches it. So this would actually be kind of off to the side, but you would solve this, well, because it's already solved for secant squared, you can put this 1 plus tangent squared in for secant squared. So you're replacing secant squared with 1 plus tangent squared x, subtracting 1, and you can see that the 1's cancel and you're just left with tangent squared x. What do you think of that?
So secant squared x is the same as 1 plus tangent squared x?
Yes, and these are the 3 Pythagorean identities that you have to know.
I think I got that.
Okay, so why don't you try 32? It's really similar. You're going to be using these identities again. I'll just put it kind of here in the middle of the screen. You've already got it on your page, but you're going to use that last one there.
So this be cotangent squared t.
Yes, or yes. So the reality is, though, you're not going to get one. You're not going to get something on the test or quiz this simple, because it really is. But this is an intermediate step that or this is something you might use in another problem, and we'll see that in 37. So I think this will make more sense when we actually use it in context. So 37 here. Whenever you see a squared, you really do want to think identities, Pythagorean identities. So that 1 minus sine squared, it should really call out to you. You should say, oh, I recognize that from my reference sheet. And I'm just stalling here to snip that in here again for you. So like whenever you see sine squared, you should think of the first one, that top one there. Now, notice it's not solved for sine squared. So you have a choice here. You can actually take that top one and solve it for 1 minus sine squared. Okay. And to do that, you're just moving the sine squared to the other side of the equation. And let me show you that here. It is sine squared theta plus cosine squared theta equals 1. Excuse me, you're subtracting sine squared theta from both sides. And so 1 minus sine squared theta equals cosine squared theta. So instead of 1 minus sine squared theta, that becomes cosine squared theta, or beta in this case, over cosine beta. Can you see that this now reduces to just cosine beta, because the one on the bottom cancels with that exponent, leaving just cosine beta like that?
Yeah.
So these 3 identities, you got to know. You got to know them really well. You got to be able to recognize them. Things like that. So let's look at 40 here. Let me snip that in. Okay. Do you see a Pythagorean identity that could be useful here in this problem?
1 plus cosine squared theta equals cosecant squared theta.
Yeah, this cotangent squared, 1 plus cotangent squared becomes cosecant squared theta, or beta. You got to use the right letter. Sine squared beta. Okay. I should have asked which side was more complicated, but I think it's pretty clear the left side is, since it's not a number. But that is the starting point. You have to decide which is more complicated. So then you go back to rewriting everything in terms of sine and cosine. It is kind of your overarching guiding strategy. So the cosecant squared is 1 over sine squared beta. Again, like, I don't know how, like, some instructors are really picky. They want you to actually write this out. Like, I would eventually just say it's 1 and be done with it. Any thoughts on that, or any concerns?
No, it's relatively simple.
Okay. Let's look at 42 next. So I will ask you which side that you feel like is more complicated.
Probably the right side.
Okay. So another way to, and so there's not really a right or wrong answer, but the kind of the way you also decide is which is easier. Is it easier to turn a plus into a multiplication? And the answer is yes. That's generally easier than a multiplication to a plus. So and you'll see that here in a moment, but we're going to actually work on the left side. You generally work on pluses or minuses rather than multiplication and divisions. Okay, but you're spot on with, like, well, multiplication is more complicated than addition, but it just happens to be that since you are converting, you have to recognize what you actually convert to. So again, just sine and cosine, that's kind of your that's your overall strategy. So cotangent is really cosine of s over sine s plus sine s over cosine s, like that. And now it looks worse. I mean, it definitely isn't easier at the moment. But there is a path here. So what do you do to combine two fractions? What's the requirement?
You have to have the denominator the same, right?
Yes. And so the denominator here, we're going to make it match it with sine and cosine. So you're going to have to multiply the one on the right by sine s, cosine s, cosine s. So in the numerator, it's cosine squared s over cosine, I guess these are s's, s sine s plus sine squared s over cosine s sine s. And now you can combine them. Now they're now you can make it one fraction up top. So cosine squared s plus sine squared s over sine usually comes before cosine, so you're going to do it that way. And then again, like, you should say, oh, I've got squareds. That's probably a Pythagorean identity.
Oh, so the top would just equal 1.
That's right. And then that's, it's really helpful. It's like, oh, the top is 1, but we got to get to, sometimes you got to bring this down. Like, how do we get it to this? How do we get to secant s cosecant s?
You multiply by the reciprocal.
You break it apart. Yeah, like the one, they're really, you can put as many ones as you want on the top and the bottom. And you will get the reciprocal, because 1 over sine is the cosecant, 1 over cosine is the cosecant. So the one on the left here is the cosecant s, and then the sine s, or secant s, and the order doesn't matter. You can flip the order. If they're really particular, then you do have to rearrange it so that it's in the right order.
Right.
So yeah, the thing to take away from this problem is generally plus and minus you work on that side first. And we'll see that again in some upcoming problem here. Like, so 44 is kind of interesting because it's got plus and minus on both sides. And you know what, it's like, well, which side do you work on? All right, so 44 here. You know, I don't know. So it really helps if you can see the transformations of the secant and the cosecant. Like if you recognize that secant is 1 over cosine, and then because you have a cosine up top over 1 over cosine, if you can see that that becomes something else, you know, that really helps here. But maybe not, you know, maybe that's, you know, not what you're seeing when you work through this. Trying to think of how else we could work through this. Yeah, we're gonna work on it this way. So this is an example of a problem where, shall I leave that, where you do have to work on both sides. But I'll point out that you cannot move anything. You can't, you know, add, subtract, multiply, divide one side to the other. So we're going to work on the left, and it's kind of what I was just showing you here. Cosine alpha 1 over cosine alpha, sine alpha 1 over sine alpha. All right. So can you tell me what these reduce to, or if you're not sure, let me know. But it's just you know, you can think of it as analogous of like x over 1 over x, or if you like numbers 2 over 1 over 2.
I'm sorry, can you give me a reminder?
Okay, yeah. So let me break them out a little bit more. So what you're doing is you're multiplying the top and bottom by the reciprocal. And so notice on the bottom, everything cancels. But on the top, you have a cosine alpha times a cosine alpha. So it becomes cosine squared alpha, like that. And so similarly, you know, you're going to have that here with the sine. You're going to multiply the top and bottom by the reciprocal. So it becomes sine squared alpha, like this. Let me bring that down. Now for these on the right here, maybe that they'll make more sense because they're numerical. But if you multiply like 2 over 1 on the bottom, 2 over 1 over top, you can see those cancel, and you get 4. X over 1, x over 1, you get x squared. Okay, so back to this. What is cosine squared plus sine squared?
That's just 1.
It's just 1, yeah. And that's not necessarily a good thing right here, because if you look at the right hand side, the right hand side is not 1. It didn't say that, you know, this equals 1. And that's where I mentioned, like, sometimes you do have to work on both sides. Okay. So the right side, I guess squareds, you typically want to use an identity. So is there an identity that stands out for you for for secant squared or tangent squared?
Secant squared.
So we're looking at these now.
Oh, they equal each other. So tangent squared theta plus 1 equals secant squared theta.
Right. That is true. You want to though substitute in one for the other. Like you either want to substitute in for secant squared or tangent squared. Since this is really solved for secant squared, I would substitute in for it. Like I would take tangent squared plus 1 and put it in for secant squared. It's taking the place of that. Is that clear or is that still not clear?
No, I get it.
Okay. There's kind of a SAT thing going on where it's a weird substitution, but it's tangent squared alpha plus 1 minus tangent squared alpha. The tangent squareds cancel, and you're left with just the 1.
So just 1 equals 1.
Yeah.
Okay.
All right, so let me know when you're ready to go into 46.
Okay.
All right, so look at this one. Which side is more complicated or complex?
Probably the left side.
Yeah, so the powers kind of give it away here. Higher degree powers are usually the side you're going to work on. So believe it or not, the left side is a difference of squares. Okay, and that formula is a squared minus b squared equals a minus b, a plus b. But what you have to figure out is what are you squaring to get back to sine to the power 4th theta? And then what are you squaring to get back to cosine to the power of 4th theta?
You'd be squaring sine or sine squared theta.
That's right.
And also cosine squared.
Right. So that's your A and that's your B. So again, just the left side, like we're not touching the right. We're just working on the left. It becomes sine squared theta minus cosine squared theta times sine squared theta plus cosine squared theta. All right, do you see anything here that simplifies or cancels or?
Sine squared theta plus cosine squared theta equals 1.
Yeah, this is 1. That's good. The left side, you might think to do the same thing we just did. You might say, oh, well, it's difference of squares again. And that's why you always have to kind of keep in mind where you're going. You're going to this 2 sine squared theta minus 1. So sometimes it's good to bring that down. It's kind of like looking at the answers on a test, multiple choice answers, like, am I there yet? Nope. So see how the answer already has a squared in it on the right? You wouldn't want to break this apart further. You'd probably want to substitute in for sine squared or cosine squared using the Pythagorean identities. Now, the one we're talking about here, I'm gonna come off to the side, I'll do it in blue here, is sine squared theta plus cosine squared theta equals 1. Since your answer has a sine squared theta in it, you want to substitute in for cosine squared because the answer doesn't have a cosine squared in it. So you have to solve this for cosine squared. You're going to subtract sine squared theta from both sides. Cosine squared theta equals 1 minus sine squared theta. This is what's going to take the place of the cosine squared theta on the left. Sorry about that. Click. So it's sine squared theta minus parentheses, because whenever you substitute, you really should do it in parentheses to not miss out on the signs. Sine squared theta minus 1 minus sine squared theta. So that's sine squared theta minus 1 plus sine squared theta, like that. And now we've got 2 sine squared theta, like that.
All right.
So, again, like kind of like sometimes you factor, but you don't keep doing it. You got to kind of always be looking at, what are you trying to get to? That's important, because if you don't know when to stop. You don't know where you're going. It's like driving and not having a target out there. So why don't you 48 through 56? I would recommend doing, well, 48 won't take that long. We can do 48.
54.
Yeah, we need to do 50 or 54, one of those, but I'll just make a comment on 48 that you just need to FOIL the left side. So you just end up, sorry, I take that back. There is more to do here. You'd want to, what would you do here? You probably need to convert this to sine squared. So you want to use that Pythagorean identity again of sine squared alpha plus cosine squared alpha equals 1. So because your answers have sines in them, you want to eliminate the cosines from the original. So your cosine squared alpha equals 1 minus sine squared alpha. So on the left here, 1 minus, and then it'd be 1 minus sine squared alpha. 1 plus 1 minus sine squared alpha. So this ends up being sine squared alpha times 2 minus sine squared alpha, and then you just multiply. And that gives you the matching thing there. Fourth alpha. Really important to pay attention to where you're going, what your answers are. Okay, so yeah, like we should just we can go through as many of these as you want, but be good to look at something in 50, 52, 54, 56. I mean, they're all good. They're all test quality questions. Any of those jump out to you? Stand out?
Probably 54.
54, okay. Right. All right. So on the left here, and we're gonna agree that the left side is more complicated, even though the right side isn't very simple. But that's the kind of, we got to make that decision early. when you see a fraction, you're immediately going to be like, I've got to make the denominators the same. So in this case, you got to multiply the 1 minus cosine s left, top and bottom on the left, 1 plus cosine s top and bottom on the right. So a lot of writing here. Tangent s 1 plus cosine s 1 minus cosine s 1 minus cosine s plus sine s 1 plus cosine s 1 minus cosine s 1 plus cosine s. As sort of a side point, I almost never use s as a variable because it really blends into the rest of it. I used to even do these with students without writing the variable, but that was also unclear. You really would just be careful, maybe, switch it up to a different letter. Now on the bottom, when you FOIL, you should recognize that the bottom is difference of squares. It's a plus b times a minus b, which becomes a squared minus b squared, meaning that you're going to square the first one, 1 squared minus cosine squared. And that's going to happen in both bottoms. Is that okay?
Yeah.
Okay. Because that is a it's the idea is to see that and then you recognize, okay, so the numerator is tangent s 1 minus cosine s over 1 minus cosine squared s. Okay, and then because they're the same bottoms, I would try to get that figured out of the done right away. Sine s 1 plus cosine s, like that. Now, does anything jump out at you about the bottom?
Um, 1 minus cosine squared s.
Pythagorean identities. That's the sine
It equals
squared.
cotangent squared.
The bottom is the first one. Sine squared s plus cosine squared s
Oh.
is 1. So then, if you were to subtract cosine squared s from both sides, you'd get sine squared s equals 1 minus cosine squared s. So the bottom, this thing down here becomes sine squared s instead of that. All right, but that's, we're still got a long ways to go. Like our answer is not very simple. Remember, our answer is cotangent s plus secant s cosecant s. So what to do from here? I'm tempted to multiply in, like sine s times both of these, tangent s times both of these. So it would be tangent s minus tangent s cosine s plus sine s sine s cosine s all over sine squared s. Is that okay up to here?
Yeah.
All right. I'm kind of looking here. I'm trying to figure out how this is going to work out nicely. The tangent s cosine s is sine s over cosine s times cosine s. So see how those cancel.
Yeah.
Okay, so that leaves minus sine s plus sine s. So those are going to cancel right there. And then you're like, all right, well, now it's getting closer. Tangent s plus sine s cosine squared, or cosine s over sine squared s. So we're gonna divide each term by the sine squared s. Right, so on the right here, on the right, you get that tangent cancels that tangent. Cosine over sine is cotangent s, and that's good because that's one of the things we wanted up here. We wanted a cotangent s and a secant s, and a cosecant. Cotangent, secant, cosecant. So we got that one. Yay, we're there. Now on the left, that tangent we break apart into sine over cosine over sine squared s. And if you just do a little rewrite here, it's really sine times 1 over cosine. And then you can put that sine squared s right there. It can go into the denominator. And then what that does is that cancels that one. So you're left with 1 over sine s, which is what we wanted. That's cosecant s. So that's your cosecant s, and that's your secant s. And there you have it.
Wow.
Yeah, kind of a monster problem. Is there a faster way to do it? Perhaps. But yeah, I mean, this works. It's just you really have to keep an eye on their target over and over again. You know, where am I going? Where am I going?
Yeah, he told us these are the types of problems that were going to be on the test.
So, you know, plan on there. I mean, you might want to ask, well, how many of these are there going to be? Because there's not going to, I mean, unless it's just verifying, I mean, you're only going to get a couple because there's other things to do, I would think at this
He'd
point.
probably give us like 3 of them.
All right. So again, like these are all kind of exam quality questions, 50, 52, 56. $59, $61. Where do you want to go next?
Can we do 59?
Sure. Okay. We looked at one earlier where the powers were bigger on one side compared to the other. These are the same. You have a plus on one side, a minus on the other. The answer actually here is it does not matter, but you should maybe, I'm trying to think what else I can say here without just telling you what to do. I guess we'll work on the left. Secant maybe is more complicated than tangent. You don't really have to have a justification for it, but what you do need to recognize is there is a GCF on the left. There's a greatest common factor between those. It's secant squared x. And that becomes secant squared x minus 1. So with that, you should say, oh, whenever I see a 1 in there, I'm really drawn to Pythagorean identities. Like this. So which one of those applies here? If you see it, if you see anything.
Secant squared x equals tangent squared x.
Plus the 1. Right. Yeah, it's really important. You really want to, like, if you look kind of at the answers though, you're like, well, I need to convert both of these to tangent. So the one on the left here is going to be tangent squared x plus 1. But then for secant squared theta, if you subtract 1 from both sides, you get tangent squared theta equals secant squared theta minus 1. That means that everything inside the parentheses in this line becomes tangent squared x. So then you can multiply these both, and you get tangent to the 4th x plus tangent squared x. So this is an example of a problem where you could actually work both sides. So what I'd like you to do is to try working the right side, and it's basically the same thing to get the left side. You're going to end up using the Pythagorean identities after you factor out. So if you don't mind, I'd like you to try that. Again, you should get the left side when you're all done.
Oh, wait. Oops. Got it.
Okay. So were you able to verify that it does work out?
Yeah.
Good. And this one's a little bit nicer because the secant squared goes right in for the one on the right, but for the one on the left, it becomes secant squared x minus 1, and then you have to multiply, and it ends up being what you expect. So that's sometimes how you can practice these. Like sometimes students are like, well, how do I even review these? And the answer is, well, it's hard, but sometimes on problems like these, you can do both sides, and especially when they kind of look equivalent. I think we had a problem like that earlier. Maybe not. Kind of. You could maybe do the same thing with this one, like 48. You could work it where you messed around with the right hand side and make it look like the left. But okay, where should we go from here?
We do 61.
Yes, let's do 61 here. So you should say, okay, the right hand side is more complicated than the left. That's pretty clear here. Now I think what they're trying to do is they're trying to help you out here by saying, like, make the common denominator on the bottom here. So like this is really 1 over 1, 1 over 1. So on the fraction on the left, you're going to multiply top and bottom by sine theta. On the left here, cosine theta, cosine theta. So you got sine theta over, this becomes sine theta minus cosine theta over sine theta. That's the common denominator there. Is that all right?
Yeah.
This is a guess. I mean, I could be, sometimes you go off in the wrong direction, and that's not always great, but here we've got cosine theta minus sine theta over cosine theta. So it kind of looks worse. It might get better. So I think what's maybe like, because there's fractions within fractions, this sine theta will end up multiplying the top one here. And then this sine theta, cosine theta will remain on the bottom. But I'm not sure if, see, the other thing we could have done, those don't match. Yeah, that's fine. So this becomes sine squared theta over sine theta minus cosine theta plus cosine squared theta over cosine theta minus sine theta. And the difference here is that you have to factor out a negative on the right or the left to make it the bottoms match. But what we could do is we could multiply the top and bottom by cosine theta plus sine theta, because what that would do is give you difference of squares. Give me just a moment here. I'll be right back. All right, I'm back. I'm not sure here because this one doesn't work out very nicely. Maybe you're seeing something. I'm going to say not to do that and to take the negative out of the bottom one here on the right. Take the negative out of that and move it to the top. So this becomes minus cosine squared theta. And then this ends up being sine theta minus cosine theta because you flip the signs. So now the bottoms are the same, but it's not, it's again, still not looking very good. So that becomes sine squared theta minus cosine squared theta over sine theta minus cosine theta. Up, now it is looking better. So this is a really tough one. The top is now difference of squares, right? It's an a squared minus b squared, like that. And so it becomes sine theta minus cosine theta, sine theta plus cosine theta, all over sine theta minus cosine theta. And look what cancels. And that gives you what you were looking for from the beginning, the sine theta plus the cosine theta. So really pretty tough, really, hard to see that from the beginning. But but just, I mean, just to give you like not to overwhelm you, but like all we really did was make a common denominator. Okay. A little flipping with fractions, factor out a negative and then use difference of squares. Like we weren't using anything exotic, we weren't using anything kind of where you might say, well, I would never think to do that. You do have to kind of work at these a bit to get there. One of the strategies that I guess I didn't talk enough about, I guess it didn't apply to that one. Real quick here on like a problem like 52, problem like 52 on the left. Let me I think that we got time to talk about this one. Definitely a lesson to where you want to practice these again. Sorry, my screen froze up here. Come on. I don't know why this is happening now all of a sudden. Okay, here we go. So this one on the left, you generally multiply by the conjugate when you've got a 1 minus situation. So you end up multiplying the top and bottom by 1 plus sine theta. And that's going to turn into difference of squares. Same thing on the right here, the 1 plus sine theta. When you multiply by 1 minus sine theta, you're going to get that difference of squares. And so the numerator becomes 1 plus sine sine theta plus 1 minus sine theta over 1 minus sine squared theta. That's your cosine squared theta on your bottom by the Pythagorean identities. The top becomes just 2 because the signs end up canceling. But the strategy here that's important is that whenever you see a 1 minus or a 1 plus, you often multiply by the conjugate. So you can see that this one here becomes 2 times 1 over cosine squared theta, which is really 2 secant squared theta, like that. So some advice I would recommend working